welcome to this problem walkthrough. Today, we'll explore an interesting problem titled Maximum Difference Between Increasing Elements. In this session, we'll break down the problem, analyze different approaches, and review key concepts to help you master this challenge. Let's get started. This problem asks us to find the maximum difference between two elements in an array, where the smaller element comes before the larger one. Specifically, given a zero-indexed integer array nums of size n, we need to identify two indices I and j such that 0 equals I less than j less than n and the value at nums, I, is less than the value at nums, j. The goal is to calculate the maximum difference as nums, j, nums, I. If no such pair exists, meaning there is no valid combination of I and j that satisfies these conditions, we return -1. The input constraints specify that the size of the array n is between 2 and 1000, and each element in the array can range from 1 to 1 billion. The output will be a single integer representing the maximum difference, or -1 if no valid pair is found. Let's consider the first example to better understand the problem. Here, the input array is nums equals 7, 1, 5, 4. The maximum difference is achieved by choosing I equals 1 and j equals 2. At these indices, nums 1 equals 1 and nums 2 equals 5. When we calculate the difference, nums 2, nums 1, results in 4, which is the largest possible difference for this array where the conditions I less than j and nums, I, nums, j, are satisfied. Therefore, the output for this example is 4. Now, let's take a look at another example to explore a different scenario. In the second example, the input array is nums equals 9, 4, 3, 2. In this case, there is no valid pair of indices, I, j, where I less than j and nums, I, nums, j. The array is strictly decreasing, meaning no element that appears later in the array is greater than any element that appears earlier. As a result, the maximum difference cannot be calculated, and the output is -1. This demonstrates that if no increasing pair exists in the array, the result will always be -1. Let's now examine a final example to see another possible outcome. In the third example, the input array is nums equals 1, 5, 2, 10. The maximum difference is achieved by selecting I equals 0 and j equals 3. Here, nums 0 equals 1 and nums 3 equals 10. When we calculate the difference, nums 3, nums 0 equals 9. This is the largest possible difference that satisfies the conditions I less than j and nums, I, nums, j, for this array. Therefore, the output is 9. Additionally, it's important to consider edge cases, such as when the array is sorted in strictly decreasing order, or all elements are the same, as these cases lead to an output of -1. For the smallest input size n equals 2, the result depends on whether the second element is larger than the first. To tackle the challenge of finding the maximum difference between increasing elements in an array, we explored two primary approaches, the straightforward brute force method and a more refined optimized approach that uses a running minimum. The brute force method is intuitive, it systematically checks all possible pairs of elements, I, j, where I comes before j. For each pair, if the second element is greater than the first, we calculate their difference and update the maximum difference if this new value is larger. The steps are simple: loop through the array, and for each starting index, check all subsequent indices to find valid differences. Finally, we return the largest difference found, or -1 if no valid pair exists. While this method is easy to understand, as we will see, it may not be the most efficient for larger inputs. The brute force approach has a time complexity of O(n squared, due to the nested loops required to evaluate all pairs, making it computationally expensive as the input size grows. However, it has a space complexity of O(1), as no additional data structures are used. This means it uses minimal memory but pays the price in execution time. The simplicity of implementation is a key advantage, it's straightforward to write and understand. However, when dealing with large arrays, the quadratic time complexity becomes a significant drawback, making this approach impractical for performance-critical applications. A more efficient solution is the optimized approach, which leverages the concept of a running minimum. The main idea is that, at any index j, the maximum difference we can achieve is determined by subtracting the smallest value encountered before j from nums, j. This allows us to avoid unnecessary comparisons. The algorithm starts by initializing min_val to the first element of the array and max_diff to -1. As we iterate through the array, we check if the current value is larger than min_val. If it is, we calculate the difference and update max_diff if the new difference is greater. If not, we update min_val to the current value. This approach ensures that we only traverse the array once, making it significantly faster than the brute force method. While the optimized approach is more efficient, it does come with a trade-off. It's slightly more complex to implement than brute force and requires an understanding of the running minimum concept, which may not be immediately obvious to all learners. The key insight here is recognizing that we don't need to compare every pair of elements. Instead, by tracking the smallest value encountered so far and calculating differences relative to it, we eliminate redundant comparisons. This simplification reduces the time complexity to O(n). The choice of this approach is driven by its efficiency, linear time complexity, constant space usage, and suitability for handling large input sizes. Once the running minimum concept is understood, the algorithm becomes straightforward and highly effective. When weighing the trade-offs between the two approaches, the brute force method stands out for its simplicity and ease of implementation. However, its inefficiency for larger arrays makes it less practical in scenarios where performance matters. On the other hand, the optimized approach achieves a much better balance between clarity and efficiency. Its linear time complexity ensures scalability for larger inputs, while its constant space usage minimizes memory overhead. In conclusion, the optimized approach is the superior choice due to its performance advantages, especially when dealing with arrays of significant size. By focusing on the core insight of tracking the running minimum, it solves the problem effectively while remaining computationally efficient. To solve the problem of finding the maximum difference between increasing elements in an array, we aim to identify two elements where the smaller one appears before the larger one, and the difference between them is the greatest possible. If no such pair exists, we return -1. The optimized approach makes use of a running minimum to keep track of the smallest value encountered so far. We start by initializing two variables, min_element, which is set to the first element of the array, and max_difference, which is initialized to -1. This ensures we handle cases where no valid pair exists. Next, we iterate through the array starting from the second element. For each element, we calculate the difference between the current element and the min_element. If this difference is greater than the current max_difference, we update max_difference to the new value. This way, we track the largest difference efficiently as we traverse the array. As we continue iterating through the array, we also update the min_element whenever we encounter a smaller value. This ensures that min_element always holds the smallest value seen so far, which is critical for calculating accurate differences. Additionally, we need to handle edge cases. For instance, if the array has fewer than 2 elements, we immediately return -1 since it's not possible to calculate a difference. Similarly, if the array is strictly decreasing, meaning no valid pair of increasing elements exists, the max_difference will remain -1, which we return. Once the iteration is complete, we return the value of max_difference as the result. This algorithm efficiently identifies the maximum difference while ensuring edge cases are handled appropriately. Key insights into this approach help us understand why it's both efficient and effective. First, by tracking a running minimum, we ensure that every difference calculation uses the smallest possible value that occurs before the current element. This eliminates the need for nested loops, reducing the time complexity from O(n)² to O(n). Second, initializing max_difference to -1 is important because it allows us to handle cases where no valid pair of increasing elements exists, as the problem specifies -1 as the return value in such scenarios. Lastly, the algorithm considers all relevant edge cases, such as arrays with fewer than 2 elements, arrays where all elements are equal, and arrays that are strictly decreasing. These considerations make the solution robust and applicable to a wide range of input scenarios. To implement this algorithm, we only need a few simple data structures. The min_element variable tracks the smallest value seen so far, and the max_difference variable stores the maximum difference found during the iteration. Beyond these two variables, the algorithm directly uses the input array without requiring any additional space. This makes the approach highly space efficient, with an auxiliary space complexity of O(1). In terms of time complexity, the algorithm is linear, or O(n), because we iterate through the array exactly once, performing constant time operations within the loop. This combination of linear time complexity and constant space complexity ensures that the solution is both fast and memory efficient, even for large input arrays. Let's walk through an example with the input array 7, 1, 5, 3, 6, 4. We start by initializing min_element to the first element, which is 7, and max_difference to -1. As we iterate, at index 1, the current element is 1, which is smaller than min_element, so we update min_element to 1. At index 2, the current element is 5. The difference between 5 and min_element, 1, is 4, which is greater than max_difference, so we update max_difference to 4. At index 3, the current element is 3. The difference between 3 and min_element, 1, is 2, which is less than max_difference, so no update is made. At index 4, the current element is 6. The difference between 6 and min_element, 1, is 5, which is greater than max_difference, so we update max_difference to 5. Finally, at index 5, the current element is 4. The difference between 4 and min_element, 1, is 3, which is less than max_difference, so no update is made. By the end of the iteration, max_difference is 5. The final output for the example array 7, 1, 5, 3, 6, 4 is 5, as this is the largest difference between increasing elements in the array. Now, consider an edge case like 5, 5, 5, 5. Here, since all elements are equal, no valid pairs of increasing elements exist, so the result is -1. Similarly, for an array like 10, 8, 7, 5, which is strictly decreasing, no valid pairs can be found, and the result is again -1. These examples demonstrate how the algorithm handles both typical scenarios and edge cases effectively, ensuring accurate results under all conditions. This implementation solves the problem of finding the maximum difference between two increasing elements in an array, where the smaller element appears first. The solution efficiently runs an O(n) time complexity by leveraging a single pass through the array, keeping track of the running minimum element and the maximum difference encountered so far. Step-by-step explanation. 1. Initialization. Min_value is initialized to the first element of the array. This variable keeps track of the smallest element encountered so far as we iterate. Max_diff is initialized to -1, which is the default return value if no valid increasing pair exists. 2. Iterate through the array. Starting from the second element, index 1, we check each number in the array. If the current number, nums, I, is greater than min_value, it means we have found a valid increasing pair. The difference is calculated as nums, I, min_value, and max_diff is updated if this difference is larger than the current max_diff. If the current number is not greater than min_value, we update min_value to the current number. This ensures that we always have the smallest possible value for calculating differences with subsequent elements. 3. Return the result. After completing the loop, max_diff contains the maximum difference found, or -1 if no valid increasing pair was found. Example walkthrough. Consider the input nums equals 7, 1, 5, 4. Initialize min_value equals 7 and max_diff equals -1. At I equals 1, nums, I, equals 1. Update min_value to 1. At I equals 2, nums, I, equals 5. Calculate the difference, 5, 1 equals 4. Update max_diff to 4. At I equals 3, nums, I, equals 4. Calculate the difference, 4, 1 equals 3. Max_diff remains 4. The final result is 4. This solution is optimal and handles edge cases like arrays with no valid pairs, e.g., 5, 4, 3, 2, 1, correctly by returning -1. This Java implementation solves LeetCode problem number 2016, maximum difference between increasing elements by using the same logic as the provided Python solution. The algorithm tracks the minimum value encountered so far and computes the maximum difference whenever a larger value is found. Key Java-specific elements include explicit type declarations, usage of Java's math.max for comparisons, and adherence to Java class structure. The method iterates through the array in O(n) time complexity, ensuring efficiency. Here, we begin with the first example where the input array is nums equals 7, 1, 5, 4. To solve this, we start by initializing two variables. The first is min_value, which is set to the first element of the array, 7. The second is max_diff, initialized to -1 since no difference has been calculated yet. Now, as we iterate through the array, we look at nums, 1, which is 1. Since 1 is less than the current min_value, we update min_value to 1. At this point, no valid difference can be calculated since the current number is smaller than the updated min_value. Next, we move to nums, 2, which is 5. This time, 5 is greater than min_value, so we calculate the difference, 5, 1, which equals 4. This is larger than the current max_diff, so we update max_diff to 4. Now, we proceed to nums, 3, which is 4. Here, 4 is greater than the current min_value of 1, so we calculate the difference, 4, 1, which equals 3. However, this difference is smaller than the current max_diff of 4, so max_diff remains unchanged. After completing all iterations, the maximum difference between any increasing pair in the array is 4. For the second example, the input is nums equals 9, 8, 7, 6. We start by initializing min_value to the first element, 9, and max_diff to -1. On the first iteration, we examine nums, 1, which is 8. Since 8 is less than min_value, we update min_value to 8. Again, no valid difference can be calculated since the current number is smaller than the updated min_value. Continuing with the example, we look at nums, 2, which is 7. Since 7 is less than the current min_value of 8, we update min_value to 7. Next, we examine nums, 3, which is 6. Once again, 6 is less than min_value, so we update min_value to 6. At the end of all iterations, no valid increasing pair exists, as every number is smaller than the one before it. This means the max_diff remains -1, which is the output for this case. For the third example, the input array is nums equals 2, 3, 10, 2, 4, 8, 1. We start by initializing min_value to the first element, 2, and max_diff to -1. On the first iteration, we examine nums, 1, which is 3. Since 3 is greater than min_value, we calculate the difference, 3, 2, which equals 1. This updates max_diff to 1. Next, we move to nums, 2, which is 10. Since 10 is greater than min_value, we calculate the difference, 10, 2, which equals 8. This is larger than the current max_diff, so we update max_diff to 8. Now, we evaluate nums, 3, which is 2. This is equal to the current min_value, so there's no change to either min_value or max_diff. Next, we examine nums, 4, which is 4. Since 4 is greater than min_value, we calculate the difference, 4, 2, which equals 2. However, this is smaller than the current max_diff of 8, so max_diff remains unchanged. Then, we move to nums, 5, which is 8. Since 8 is greater than min_value, we calculate the difference, 8, 2, which equals 6. Again, max_diff remains 8. Finally, we evaluate nums, 6, which is 1. Since 1 is less than min_value, we update min_value to 1. After completing all iterations, the maximum difference between any increasing pair in this array is 8, which is the final output. The time complexity of this solution is O(n), where n is the length of the input array nums. This is because we iterate through the array exactly once using a single for loop. The loop runs from index 1 to n1, which means it processes all elements except the first one. Each iteration of the loop involves only constant time operations, such as comparisons, subtractions, and updating variables. Since the loop runs n1 times and each operation inside the loop is O1, the total time complexity simplifies to O n1 asterisk O1, which is equivalent to O n. This makes the algorithm linear in complexity, meaning its runtime scales directly with the size of the input array. The space complexity of the solution is O1, which means it uses constant space regardless of the size of the input array. This is because the algorithm only uses two variables, min_value, which tracks the smallest number encountered so far, and max_diff, which stores the maximum difference between increasing elements. These variables do not grow with the size of the input, and no additional memory is allocated for other data structures like arrays or hash maps. Since the input array nums is only read and not modified or copied, the overall memory usage remains constant, resulting in a space complexity of O1. When analyzing the algorithm across different cases, we see that its behavior remains consistent. In the best case, where the array is already sorted in increasing order, the algorithm still iterates through the entire array and performs the same constant time operations per iteration, leading to a time complexity of O(n) and space complexity of O(1). Similarly, in the average case, the total number of iterations and comparisons remains the same, so the time complexity is still O(n), and the space complexity remains O(1). In the worst case, where no valid pair exists, such as when the array is sorted in non-increasing order, the algorithm still processes every element, resulting in the same O(n) time complexity and O(1) space complexity. Thus, the algorithm is efficient and consistent across all scenarios. To understand the efficiency of this solution, it's helpful to compare it with the brute force approach. In a brute force method, we would check all possible pairs of elements, I, j, where j greater than I to find the maximum difference between increasing elements. This involves two nested loops, the outer loop iterating over all elements of the array, which is O(n), and the inner loop iterating over the remaining elements after the current element, which is O(i). The total time complexity for this approach sums up to O(n squared). In contrast, the optimized solution avoids unnecessary comparisons by keeping track of the smallest number encountered so far, min_value, and calculating differences in a single pass through the array. As a result, it reduces the time complexity to O(n), which is significantly faster for large inputs. The optimized solution's big O complexity can be proven by analyzing the operations step by step. The main operation is iterating over the input array, which takes O(n) time since we process each element exactly once. Inside the loop, the operations performed, such as comparisons and subtractions, are constant time operations, or O(1), for each iteration. Since the loop runs n1 times and each iteration involves only O(1) work, the total time complexity is O(n1 O(1), which simplifies to O(n). Additionally, the algorithm does not require any extra memory beyond a few variables used to store intermediate results, making the space complexity constant, or O(1). This efficient use of time and space ensures that the solution is well suited for large input sizes. One of the most common mistakes in this problem is not properly resetting the minimum value as you traverse the array. The running minimum must be updated each time you encounter a smaller element, otherwise, the differences calculated might be based on an outdated value, leading to incorrect results. Another frequent error is confusing the order of elements. Remember, the larger element must come after the smaller one in the array, so calculating the difference in the wrong order violates the problem's constraints. Additionally, many beginners use nested loops to compare every pair of elements, which results in an inefficient O(n squared) solution. While this approach works for small arrays, it becomes impractical for larger inputs due to time limits. Lastly, it's crucial to handle cases where no valid differences exist, such as when the array is strictly decreasing. In these scenarios, your function should return a default value, like 0 or -1, to avoid runtime errors or unexpected behavior. Now, it's important to address edge cases. Arrays with fewer than two elements, arrays with duplicate values, or arrays where all elements are the same can easily disrupt poorly implemented solutions. These scenarios need special consideration to ensure your approach is robust. From an interview perspective, this problem highlights the importance of pattern recognition. Specifically, the running minimum or prefix optimization technique is a foundational concept that applies to many similar array problems. Understanding this can significantly improve your ability to solve such problems efficiently. Additionally, this problem is a great example of space versus time trade-offs. While the brute force approach avoids extra space, the optimized solution uses constant space and achieves much better time complexity. Be ready to explain your choice during an interview. It's also good practice to discuss edge cases with your interviewer before coding. For example, what should the function return for an input where all elements are decreasing, like 5, 4, 3? Lastly, interviewers may pose follow-up variations. For instance, how would you modify your solution if you could skip at most one element? Or, how would you handle a stream of numbers instead of a static array? This problem also connects to several related problems on LeetCode. For example, best time to buy and sell stock, LeetCode 121, is a closely related problem, but it focuses on maximizing profit rather than the difference between elements. Another related problem is maximum subarray, LeetCode 53, which applies a similar optimization strategy, often referred to as Cadon's algorithm, but uses running sums instead of differences. Best time to buy and sell stock 2, LeetCode 122, introduces a variation where multiple transactions are allowed, requiring a different strategy to solve. Lastly, the longest increasing subsequence problem, LeetCode 300, deals with increasing elements as well, but the goal is to find the length of the longest sequence rather than the difference between values. Exploring these problems can deepen your understanding of optimization techniques and their applications. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach involves iterating through all pairs of elements where the second index comes after the first, calculating the difference for each pair. While this method is straightforward, it has a time complexity of n squared, making it inefficient for large arrays. In contrast, the optimized approach uses a running minimum. As you traverse the array, you keep track of the smallest value encountered so far and calculate the difference with the current element. This method is highly efficient, with a time complexity of n and a space complexity of 1. However, it requires careful implementation to avoid common pitfalls, like forgetting to update the running minimum. Another alternative is the divide and conquer approach, where the array is split into two halves. You calculate the maximum difference in each half and also consider differences that span across the two halves. This method has a time complexity of n log n and a space complexity of log n due to the recursive stack. While not as efficient as the optimized approach, it can be useful for understanding divide and conquer strategies in general. Great job working through this problem. To wrap up, we reviewed the problem, explored key approaches, and highlighted important takeaways. Remember, thoughtful practice and understanding trade-offs are essential to mastering algorithmic problems. Thanks for joining, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!